Tonight, we're going to look at the question that has quietly unsettled astronomers for decades. Where is everybody? There are hundreds of billions of stars in this galaxy alone. Many of them are older than our sun. Many of them have planets. The math says the odds of us being the only intelligent civilization in all of that should be vanishingly small. And yet, here we are, alone. And when you follow what it would actually take for anyone to cross interstellar space and arrive here, the answer is not what most people expect. It's a problem that compounds, layering one impossibility on another, each one requiring a solution that makes the next one even harder. By the end of tonight, you're going to understand exactly why no one has shown up, and why the deeper you look at the physics, the clearer it becomes that they probably never will. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Milky Way is 100,000 light-years across. It's a flattened spiral of somewhere between 200 billion and 400 billion stars, slowly rotating in the dark. We sit on one of its outer spiral arms, about 26,000 light-years from the galactic center. The galaxy extends another 76,000 light-years beyond us in the other direction. To cross it from edge to edge, a beam of light would need 100,000 years. A photon, traveling at 186,000 miles per second, takes 100 millennia just to complete that crossing. That's the playing field. That's the arena inside which any alien civilization trying to visit us would have to operate. And most people, when they imagine aliens visiting Earth, imagine something that crosses this casually. A ship that warps from one star system to the next. A technology so advanced it makes the distance irrelevant. That's understandable. It's the premise of almost every science fiction story involving contact. Someone figured out the shortcut. The problem is that the physics, as best we currently understand it, offers no shortcut. What it offers instead is a series of barriers so severe, so stacked on top of each other, that navigating through all of them requires technologies that don't exist, energy sources we've never produced, and timescales that outlast civilizations. And the thing is, those barriers aren't peculiar to us. They apply to everyone in the universe equally. Whatever star system you're starting from, whatever star system you're trying to reach, you're dealing with the same physics. The same speed limit, the same geometry, the same brutal math. The first barrier, and the most fundamental one, is distance. Not distance in the casual sense, where you acknowledge something is far away and move on. Distance in the sense that it is the actual, operational problem. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. That means light, moving at 186,000 miles per second continuously, takes 4 years and 3 months to travel from there to here. In miles, that's roughly 25 trillion miles. The fastest object humanity has ever launched, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour during its closest approaches to the Sun. At that speed, aimed directly at Proxima Centauri, it would arrive in roughly 6,700 years. That's our fastest thing, to the nearest star. And Proxima Centauri is the next-door neighbor in galactic terms. After that comes Barnard's star at about 6 light-years. Within 10 light-years of Earth, there are only a handful of star systems. As you extend that radius, the numbers grow. Within 100 light-years, several thousand stars. within 1,000 light-years. Millions. The galaxy has between 200 billion and 400 billion stars spread across a disk 100,000 light-years wide and a few thousand light-years thick. Most of them are very far away. Not just metaphorically, in the specific sense that the travel times, even at the most optimistic speeds any physically grounded propulsion system could achieve, are measured in decades, centuries, and millennia. People push back on this with a reasonable objection. They say a civilization millions or billions of years more advanced than us would have solved this. They'd have drives we can't imagine. They'd have mastered energy at scales beyond our comprehension. And that's a genuinely fair point. We absolutely should not assume that our current technology defines the ceiling of what's physically possible. History has proven that wrong too many times. But here's the critical distinction. The ceiling isn't set by our technology. It's set by physics. And physics doesn't have a different rulebook for advanced civilizations. The relevant constraint here is the one Albert Einstein articulated in 1905 in his theory of special relativity. It says that nothing with mass can be accelerated to the speed of light, not because we haven't figured out how, but because the mathematics of space-time itself forbids it. As you accelerate any object with mass toward the speed of light, the energy required doesn't increase linearly. It increases toward infinity. At 50% of light speed, a spacecraft's relativistic mass is about 15% higher than its rest mass. At 90%, more than double. At 99%, about 7 times. At 99.9%, about 22 times. At 99.99%, about 70 times. The closer you get, the more energy you need just to gain the next tiny increment of speed. To actually reach the speed of light would require infinite energy. Infinite energy doesn't exist anywhere in the universe. This isn't a statement about our limitations. It's a statement about the universe's fundamental structure. A civilization 1 billion years more advanced than us is still constrained by this. The wall doesn't move for anyone. No amount of technological progress can make infinite energy available, because infinite energy is not something that exists in this universe to be harnessed. What this means in practice is that any spacecraft, from any civilization anywhere in the universe, traveling between stars, is going to take years to arrive, at best. Probably decades or centuries, depending on where they started and what speeds are achievable. That's not a footnote. That's the defining feature of the problem. Physicists have proposed warp drive, and it comes up every time this conversation happens. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper presenting a mathematical solution to Einstein's field equations that seemed to offer a way around the light-speed barrier. The concept was elegant. Instead of moving a spacecraft through space, what if you move space itself? Specifically, contract the space in front of the spacecraft and expand the space behind it. The ship would sit inside a bubble of flat space-time. The bubble would move through the curved space-time around it. And crucially, from the perspective of an outside observer, the bubble and its contents could move faster than light because the space-time itself was moving. The ship wasn't moving through space. The space was moving. This is not prohibited by special relativity in the same way that direct faster-than-light travel is prohibited. Special relativity says nothing with mass can move through space faster than light. It doesn't explicitly say space-time itself can't move faster than light. Alcubierre's paper was mathematically valid. It satisfied Einstein's field equations. It was published in a respected journal, and it generated enormous excitement. But immediately, problems became apparent. The first and most serious was the energy requirement. To create the warp bubble, the mathematics required something called exotic matter. Specifically, matter with negative energy density. In normal physics, the energy density of any region of space is positive. Even empty space has a small positive energy density from quantum fluctuations called the vacuum energy, or the cosmological constant. Negative energy density, matter that somehow contributes a negative amount to the total energy budget of a region, is an extraordinary requirement. It's theoretically permitted by some interpretations of quantum field theory. The Casimir effect, where two uncharged metal plates placed very close together experience a tiny attractive force due to quantum vacuum fluctuations, is sometimes cited as an example of negative energy. Between the plates, the vacuum energy is slightly lower than outside, which could be interpreted as a negative energy density difference. But the amount of negative energy involved in the Casimir effect is minuscule. The amount required for an Alcubierre warp bubble was, in early calculations, roughly the mass energy of Jupiter. In exotic matter. Later refinements by Krasnikov and others brought that number down, sometimes substantially. But even the most optimistic later estimates required exotic matter in quantities that far exceed anything ever observed or produced. And they required it to have properties, specific distributions in space around the bubble that impose further constraints. There have been other developments since. In 2024, physicist Harold Fuchs published a paper describing a class of warp metrics that use only ordinary positive energy. No exotic matter required. This was a genuine mathematical result. Real physics. Published in a real peer-reviewed journal. It showed that warp-like curvature of spacetime, technically called a warp spacetime, doesn't necessarily require exotic matter. But Fuchs was careful, in every interview and in the paper itself, to spell out the critical limitation. His design is subluminal. The bubble, it describes, moves slower than the speed of light. It does not enable faster than light travel. It demonstrates that the warp effect is mathematically achievable without exotic matter, but not at superluminal speeds. For the purpose of visiting Earth from another star system, a subluminal warp bubble offers no fundamental advantage over any other propulsion system. You still take years to get to Proxima Centauri. You still take decades or centuries to get to anything interesting farther away. The faster-than-light versions of warp drive, every design proposed so far, require energy conditions that appear to be physically impossible, not just practically difficult. Quantum field theory imposes what physicists call energy conditions, constraints on how energy is distributed in spacetime. Faster-than-light warp geometries tend to violate those conditions. Proving this conclusively across all conceivable warp designs is an ongoing research problem. But the evidence accumulated over 30 years of work following Alcubierre's original paper is not encouraging for superluminal travel. Short version: warp drive is not available. Not to us. Not to anyone, as best we can determine. And the constraints don't relax based on how advanced you are. They're set by physics. Let's get precise about the energy problem, because it's the most immediate practical barrier. The rocket equation, named after Konstantin Tsiolkovsky, who derived it in 1897, describes the relationship between the fuel you carry and the velocity you can achieve. It's not a linear relationship. It's exponential. For every increment of additional velocity you want, you need a disproportionately larger amount of fuel. And you have to carry all that fuel from the start, which means you have to accelerate the fuel along with the payload, which requires more fuel to accelerate the fuel, which requires more fuel still. The cascade is brutal. For chemical rockets, the exhaust velocity is limited by the chemical energy available in the reaction. Hydrogen and oxygen combustion, one of the most efficient chemical reactions, produces exhaust velocities of roughly 4,500 meters per second. To reach interstellar speeds, you need exhaust velocities, orders of magnitude higher. Nuclear thermal propulsion, where a nuclear reactor heats propellant to much higher temperatures than chemical combustion can achieve, provides exhaust velocities of roughly 10,000 meters per second. Better. Still, nowhere near interstellar requirements. Nuclear pulse propulsion, the Orion concept where nuclear explosions drive a shock absorber plate at the back of the spacecraft, could theoretically achieve exhaust velocities 10 to 100 times higher than chemical rockets. If the engineering could be made to work, which is a large if, nuclear pulse could potentially accelerate a spacecraft to several % of light speed. Not enough for a journey of decades. For nearby stars, yes. But with extreme time requirements and a spacecraft design that involves detonating nuclear warheads at regular intervals behind you, fusion propulsion, if achieved, would provide dramatically higher performance. Fusion reactions release energy through the combination of light atomic nuclei, primarily hydrogen isotopes, into heavier nuclei. The energy release per unit mass is orders of magnitude greater than fission. A fusion rocket, if it could be built, might achieve exhaust velocities of 5 to 10% of light speed. That would make interstellar voyages feasible in principle, though still taking decades for the nearest stars. The problem is that sustained controlled fusion has been pursued since the 1950s, and we haven't achieved it for practical energy generation yet, let alone for compact rocket engines. Antimatter propulsion represents the theoretical optimum. When matter and antimatter annihilate, they convert 100% of their mass to energy. Einstein's E equals mc squared. No other reaction approaches that efficiency. A gram of antimatter, annihilating with a gram of matter, releases energy equivalent to roughly 43 kilotons of TNT. All the antimatter ever produced in all of Earth's particle accelerators combined amounts to a tiny fraction of a microgram. And every bit of it was immediately annihilated in the production process. We've never stored any. Storing antimatter requires suspending it in magnetic fields, with no contact with normal matter. Any failure of the containment system destroys the antimatter immediately. The energy cost of producing antimatter through particle accelerators is far greater than the energy released by annihilation. We're not close to antimatter production at scales relevant for propulsion. Not by orders of magnitude. And even with perfect antimatter propulsion, the fuel mass required for a meaningful interstellar voyage, carrying a crew, life support, scientific equipment, return fuel, still runs into the rocket equation problem. The efficiency is unmatched, but it's not infinite efficiency. You still have to carry the fuel. You still have to accelerate the fuel along with everything else. The rocket equation still applies. Then comes the deceleration problem, which is so obvious, yet so consistently underemphasized. Getting to speed is only half the journey. Space has no friction. There is nothing in the interstellar void to slow you down. If you accelerate to 10% of light speed and then shut off your engines, you stay at 10% of light speed indefinitely. When you reach your destination star system, you blow through it in days or weeks, still traveling at 10% of light speed, and continue into the void on the other side. To enter orbit around a planet, to slow down enough to conduct any meaningful mission, you have to reverse your thrust and decelerate. Cancel out all that velocity you built up. This requires the same energy as acceleration. The same fuel, the same time. All of those carefully calculated rocket equation ratios doubled. If you want to return home afterward, doubled again. A round trip to the nearest star, at speeds that make the outbound journey take a human lifetime or less, requires energy reserves and fuel quantities that exceed anything any civilization has demonstrably produced. Some designs propose using the destination star itself for braking. A magnetic sail interacting with the stellar wind, a cloud of charged particles streaming outward from the star, can provide drag and bleed-off velocity over years of approach. If there's a gas giant conveniently placed multiple passes through its upper atmosphere, using atmospheric drag to slow down without fuel, aerobraking can work in principle. Laser-driven light sails, where a powerful laser array at the home star pushes a sail to accelerate, can potentially be reversed using a mirror at the destination to redirect the laser for deceleration. Each of these proposals adds constraints and complexity. They all require the destination star system to have convenient features. They all take additional years of flight time. They all have failure modes that are catastrophic and unrecoverable from interstellar distances. But they're, at least, physics consistent. They don't require anything that violates known laws. The fundamental problem remains that stopping at the end of an interstellar journey is just as hard as starting it. Harder, really, because you're now deep in an unfamiliar star system with less redundancy and no nearby support. Time dilation is one of the most counterintuitive consequences of special relativity. And it's worth understanding in detail because it's often presented as a potential workaround for the travel time problem. The argument goes, yes, an interstellar journey takes decades by Earth's clock, but due to time dilation, the crew experiences far less time. So a crew that subjectively spends 10 years in transit could arrive at a star system that is more than 100 light-years away. This is real physics. Time genuinely does pass more slowly for objects moving at high speed relative to a stationary observer. The faster you travel, the greater the dilation. At 10% of light speed, clocks on the ship run at about 99.5% the rate of clocks on Earth. Small effect. Almost negligible. At 50% of light speed, clocks on the ship run at about 87% of Earth's rate. More noticeable. At 90% of light speed, clocks run at about 44% of Earth's rate. At 99% of light speed, clocks run at about 14% of Earth's rate. If you could get to 99.9% of light speed, clocks would run at about 4.5% of Earth's rate. For a ship traveling at that speed, the subjective journey to Alpha Centauri would take only a few months, even though Earth's clocks would show it taking over 4 years. This does appear to help with the crew survival problem. The crew ages less. They experience less time in transit. Their subjective experience of the voyage is shorter. But the problems with this solution are layered. First, reaching 99.9% of light speed requires extraordinarily more energy than reaching 10% of light speed. We're talking about energy requirements many orders of magnitude larger. Even with antimatter propulsion at 100% efficiency, the fuel mass required to accelerate a meaningful payload to 99.9% of light speed and then decelerate it at the destination is overwhelming. The rocket equation is merciless here. The more speed you want, the more fuel you need. The more fuel you carry, the more mass you're accelerating. The more mass you're accelerating, the more fuel you need for that. The cascade reaches points where even very efficient propulsion systems can't plausibly build a crewed spacecraft with a useful payload fraction. Second, the time dilation helps the crew. But Earth doesn't experience time dilation. While the crew subjectively spends a few years in transit, Earth experiences the full light travel time plus any additional transit time. A ship traveling to a star 100 light-years away at 99% of light speed takes just over 100 years from Earth's perspective. The crew might age 14 years. But Earth ages over 100. When the crew arrives, everyone they knew is almost certainly gone. The civilization that sent them has changed dramatically. Any mission objectives that depended on returning to a civilization similar to the one they left are compromised. Third, time dilation at high speeds exacerbates the particle impact problem. At 99% of light speed, each interstellar hydrogen atom encountered carries vastly more kinetic energy relative to the ship. The radiation environment becomes more severe. The shielding requirements become more extreme. The energy deposited in the shield material per unit time increases. The structural stresses on the forward shield are greater. Time dilation helps with crew aging, but it doesn't help with anything else. And achieving the speeds needed for significant time dilation introduces new problems, at least as severe as the ones it solves. Let's think about what it takes biologically to survive an interstellar voyage. Suppose all the engineering problems were solved: the energy, the propulsion, the shielding, the navigation. The crew still has to survive. And human biology was calibrated by billions of years of evolution for a very specific environment: Earth's surface, Earth's gravity, Earth's atmospheric composition, Earth's light cycle, Earth's temperature range, Earth's microbial ecosystem, which coexists with our biology in extraordinarily complex ways. None of those conditions exist naturally in interstellar space. Start with gravity. On Earth, gravity is 1g, one standard unit of gravitational acceleration. Your bones, your muscles, your cardiovascular system, your inner ear, everything about how your body works is calibrated to function in this environment. Remove gravity and things go wrong fairly quickly. Fluid shifts toward the head because there's no gravity pulling it downward. The body interprets this as excess fluid and responds by reducing blood volume, which has cascading effect. Bone density decreases because the mechanical stresses that maintain bone strength disappear. The process of bone remodeling, constantly balancing bone deposition and resorption, shifts toward net resorption in the absence of load-bearing mechanical stress. Muscle mass decreases for the same reason. Without the constant work of holding yourself upright against gravity, walking, climbing, muscles atrophy. Even with rigorous exercise routines designed specifically to minimize these effects, astronauts on long-duration missions to the International Space Station return with measurable decreases in bone density and muscle mass. 6-month missions to the space station, which is still in Earth's orbital neighborhood, but essentially microgravity due to continuous freefall, produce changes that require months of recovery on return. For a voyage lasting decades, the cumulative effects would be far more severe, and they wouldn't be reversible in the same way. A crew spending 40 years in microgravity would arrive at their destination with bodies that have adapted, in problematic ways, to the absence of gravity. Their bones would be weaker. Their cardiovascular systems would have adapted to reduced demands. Their sense of spatial orientation and balance would have reorganized around a non-gravitational environment. Reintegrating into gravity at the destination would itself be a significant physiological challenge. Rotating spacecraft can provide artificial gravity through centrifugal acceleration. Spin a large enough cylinder, fast enough, and the occupants on the outer rim experience something analogous to gravity. This solves some of the microgravity problems, but it introduces others. The Coriolis effect, the apparent deflection of motion in a rotating frame, can cause disorientation. The required rotation rate and radius to simulate Earth gravity is large enough that spacecraft engineering becomes much more complex. Structural stresses on a large rotating habitat are significant. Constructing one in space, launching it, and maintaining it for decades without failure requires engineering capabilities we haven't demonstrated. It's solvable in principle, but it adds to the stack of challenges that have to be solved simultaneously. Let's think about what interstellar space actually feels like, phenomenologically, because it helps ground what we're asking any ship to traverse. The interstellar medium is the material that fills the space between stars in our galaxy. It's not a uniform substance. It varies enormously from place to place. Some regions are relatively dense clouds of gas and dust. The Orion Nebula is a famous example, a stellar nursery where new stars are forming from compressed clouds of hydrogen and helium. Other regions are extraordinarily sparse. Hot ionized plasma, blown outward by supernovae, the local bubble we happen to live inside, a roughly spherical region about 300 light-years across, excavated by one or more ancient supernova explosions. On average, the interstellar medium contains about 1 particle per cubic centimeter. A cubic centimeter is roughly the size of a sugar cube. In that volume, in interstellar space, there's typically 1 atom. The air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. So, interstellar space is about 25 quintillion times emptier than air. That sounds like a vacuum, so perfect as to be irrelevant for any ship moving through it. And at everyday speeds, it essentially is. The Voyager probes have been traveling through it for nearly 50 years without the interstellar medium causing any significant issues. But at 10% of light speed, the interstellar medium changes character. At that velocity, a ship would be sweeping through interstellar space at roughly 60 million miles per hour. In 1 second, it traverses about 18,000 miles. In a year, it covers about 500 billion miles. In each cubic centimeter of space, it passes through, on average, 1 hydrogen atom. At those speeds, hydrogen atoms don't gently brush against the hull. They hit with relativistic energies. Each individual atom's impact is tiny. But, across the full face of the ship, across trillions of impacts per second, the cumulative radiation dose and material erosion become significant. The interstellar medium also isn't uniform. There are denser clouds. If a ship at 10% of light speed passed through even a modestly denser region, the effects on the hull and the radiation dose inside would increase substantially. Navigation around denser regions is possible in principle, but it requires knowing where they are far enough in advance to change course. At 10% of light speed, you're traveling so fast that course correction itself requires significant thrust. And you need to know what's ahead. A star-forming region, a nebula, a dense gas cloud could be hundreds of light years away and still pose a navigation hazard if your trajectory passes through it. The interstellar medium is also not static. It moves. It's stirred by stellar winds, supernova shockwaves, and the orbital dynamics of the galaxy. What's along your planned trajectory when you launch might be different by the time you get there. Predicting the state of interstellar space along a path that takes decades to traverse requires understanding the dynamics of the interstellar medium on those timescales. That's an active area of astrophysics research. We're getting better at it. But it's another layer of complexity that makes mission planning genuinely difficult. Then there's radiation. Interstellar space is permeated by cosmic rays. High-energy particles, mostly protons, and heavier atomic nuclei, accelerated to close to light speed by supernovae, neutron star collisions, and the active environments around black holes. These particles travel through the galaxy in all directions, constantly, and they pass through solid matter. On Earth, the planet's magnetic field deflects many of them. The atmosphere absorbs the cascades of secondary particles produced when the most energetic ones do get through. Below Earth's surface, you'd receive almost no cosmic radiation at all. In interstellar space, there's no magnetic field and no atmosphere. You're exposed directly to everything the galaxy can throw at you. And the galaxy throws quite a lot. Cosmic rays span an enormous range of energies. At the lower end, a few hundred mega-electron volts, shielding can be effective. At higher energies, particles punch through meters of material with relative ease. The most energetic cosmic rays ever measured, called ultra-high-energy cosmic rays, carry macroscopic amounts of kinetic energy in a single particle. Enough to feel on your fingertip if you could hold one still, which you can't because they travel at fractionally below light speed. These high-energy particles can't be stopped by any practical amount of shielding. The lower-energy cosmic rays, which are more numerous, can be reduced significantly by shielding. Water is effective. Hydrogen-rich polymer materials work well. A spacecraft surrounded by water tanks would reduce the dose inside substantially. But you can't carry enough water to stop everything. And every kilogram of water is a kilogram you have to accelerate to interstellar speed and decelerate at the destination. The mass budget for shielding trades directly against the mass budget for everything else. The radiation dose for a crew on a 40-year interstellar voyage, even with heavy shielding, would be large enough to substantially increase cancer risk. Estimates suggest that a Mars mission, which would take roughly 8 to 9 months in deep space each way, would expose crew members to doses approaching the career limits recommended for professional astronauts. An interstellar voyage would multiply that exposure by a factor of many. Long-term exposure also affects the central nervous system in ways that are still being characterized. Studies of mice exposed to simulated cosmic radiation show cognitive changes, including problems with memory and spatial reasoning. These effects haven't been studied in humans over the relevant timescales, because no human has been exposed for that long. We're modeling based on rodent studies and extrapolation from what we know about radiation effects. The uncertainty is significant. There's also a solar radiation component. During solar events, coronal mass ejections that blast charged particles into space at high speed, the radiation environment spikes dramatically. Inside Earth's magnetosphere, these are mostly harmless. In interstellar space, a major solar event from your home star could be dangerous, even if you're years away, if the particles travel fast enough. The radiation problem is real, documented, and does not go away just because a civilization is more advanced. The particles are the particles. They carry the energy they carry. Advanced materials science might produce better shielding, but the fundamental physics constrains how much shielding can help. The micrometeorite and debris problem scales in a way that's deeply counterintuitive. At everyday orbital speeds, around 17,000 miles per hour for low Earth orbit, a grain of sand hitting your spacecraft is a minor concern. At 10% of light speed, that same grain of sand hits with energy comparable to a sizable explosive. Kinetic energy is proportional to mass times velocity squared. 10% of light speed is 18,600 miles per second. That's about 4,000 times faster than orbital velocity. Kinetic energy at 10% of light speed is about 16 million times higher than at orbital velocity for the same mass. A dust grain weighing a microgram, a millionth of a gram, at 10% of light speed carries about the same kinetic energy as a small explosive device. A particle a millimeter across, about the mass of a small grain of sand, carries energy comparable to a large bomb. The interstellar medium isn't truly empty. It contains, on average, about 1 atom per cubic centimeter. That's very sparse compared to anything we experience on Earth. But over 25 trillion miles, even that sparse medium accumulates. More importantly, it isn't uniformly sparse. There are denser regions, gas clouds, dust clouds, the remnants of supernovae, that are far more populated. Navigating through a denser region at interstellar speed would be catastrophic without extraordinary shielding. Even in relatively empty space, the accumulated exposure to interstellar medium particles over a 40-year journey at 10% of light speed is not negligible. The spacecraft needs a shield at its leading face. A sacrificial layer of material thick enough to ablate incoming particles before they reach the main structure, but not so thick that it makes the mass budget unworkable. This shield is slowly destroyed during the voyage. Its depth decreases as impacts vaporize material from its surface. It might need to be regenerated somehow, which means either carrying mass for that purpose or having some in-flight fabrication capability. Detection and avoidance of larger objects is another challenge. At 10% of light speed, you're traveling roughly 18,000 miles per second. An object detected 100 miles ahead gives you less than 6,000ths of a second to react. No human reaction time is adequate. The ship's systems would need to autonomously detect and respond in microseconds. In theory, advanced sensors could detect objects farther ahead. A pebble-sized rock in space is nearly impossible to detect at any range against the background of deep space using any sensor technology we currently have. Advanced radar, LiDAR, electromagnetic sensors of various kinds might extend detection range. But at the speeds involved, even large detection ranges leave very small response windows. The physics of the particle impact problem is the same for any civilization attempting interstellar travel. Mass, velocity, kinetic energy. The math is the same for everyone. Navigation compounds these challenges in ways that get underappreciated. Space is not static. Every object in it is moving. Our Sun orbits the galactic center at roughly 500,000 miles per hour. Other stars have their own individual velocities relative to both the galactic center and each other. Proxima Centauri is currently moving toward us due to its particular orbital path, which is why calculations show it will be somewhat closer in about 27,000 years before receding. A spacecraft launched toward Proxima Centauri cannot aim at where Proxima Centauri is today. It has to aim at where Proxima Centauri will be when it arrives. For a 42-year voyage, that's Proxima Centauri's position 42 years from now. The calculation is doable. We know Proxima Centauri's proper motion well enough to make that prediction. But it requires knowing the target's current velocity and trajectory to the precision needed to project a position decades into the future and guarantee arriving at the right place. For more distant targets, our velocity measurements are less precise. A small error in measured velocity translates into a larger error in predicted position over a longer voyage. A trajectory error that is undetectable at the start of the mission becomes significant over decades of travel. Course corrections in flight require propellant. Each correction burns fuel. Fuel is finite. And communications during the voyage are subject to the light speed delay. If you're 10 light years from Earth and you detect that you need a course correction, you can send a message and Earth can respond. But the message takes 10 years each way. 20 years, round trip. Whatever guidance Earth sends is responding to a situation that has already changed significantly. You're navigating on your own. Whatever you decide with the information and computation available on the ship. This is manageable for a mission with a well-defined navigation plan and robust onboard computation. But it's another layer of the challenge that has to be engineered and planned for. The communication problem during a voyage is more severe than most people appreciate. We've talked about the time lag, but there are other dimensions. At interstellar distances, radio signals spread out following the inverse square law. A signal that's strong enough to communicate clearly at a distance of 1 light year becomes 16 times weaker at 4 light years. At 10 light years, 100 times weaker. At 100 light years, 10,000 times weaker. Transmitting data from an interstellar spacecraft back to Earth, or from Earth to the ship, requires either enormous transmitter power or extremely sensitive receivers. As the ship moves farther away, you need more power or bigger antennas. Eventually, practical communication becomes very difficult. The Voyager probes, which are only a small fraction of a light year from Earth after nearly 50 years of travel, require the Deep Space Network's massive antennas and low data rate transmission to maintain contact. A spacecraft at interstellar distances transmitting useful amounts of data would require both extraordinary transmitter power and an Earth-based receiving infrastructure far beyond what we have. And as the ship recedes, every year its communications become harder. By mid-voyage, regular communication with Earth might have degraded to intermittent narrow bandwidth transmissions. Updates and guidance from home would be infrequent. The crew would be increasingly on their own in terms of real-time support, and the content of those communications would be increasingly time-lagged. News from Earth, several years old. Scientific updates from a civilization that has changed. Responses to questions the crew no longer remembers asking. The ship and its civilization of origin would gradually drift apart psychologically as well as physically. The psychological challenge of an interstellar voyage deserves its own extended examination. Humans are social animals. We evolved in groups. We need connection, novelty, variety, and the experience of space and nature. Our brains are calibrated to an environment with horizon lines, weather, seasons, other living things, and the simple sensation of sunlight and fresh air. None of those exist on a spacecraft in interstellar space. The artificial environment of a spaceship provides controlled light cycles, temperature, and atmospheric composition. But it provides no natural light variation. No weather, no seasons, no horizon, no wildlife, no random encounters with other people. Every person you interact with is someone you already know, already work with, already live with. The social universe is completely closed. In psychological research on extreme environments, isolation, confinement, and monotony are among the most destructive factors for mental health and cognitive function. Antarctic winter overstations have documented the psychological effects of months of isolation in a small group. These effects are real and significant, even in relatively comfortable conditions, with regular communication with the outside world and with the certain knowledge that the isolation will end. For a crew on a 40-year interstellar voyage, none of those mitigating factors apply. Communication with Earth becomes increasingly intermittent and delayed. The isolation has no certain end within any individual's lifetime. The monotony of spacecraft life is alleviated by mission activities, but those activities don't provide the variety and spontaneity of life on a planet. Interpersonal dynamics in confined groups are well documented in psychology and sociology. When people can't leave an environment, minor conflicts become magnified. Personality friction that would be easily managed by simply spending less time together becomes a persistent stress. Social hierarchies emerge and can become oppressive. Group thinking can develop in ways that suppress dissent and lead to poor decisions. In a small crew on a critical mission, these dynamics have potentially catastrophic consequences. A conflict that fractures the group, a leader whose decisions go unchallenged due to power dynamics, a failure of morale that reduces the crew's ability to function effectively. Any of these could compromise the mission. The psychological screening and management protocols for interstellar crew selection and support would have to be more sophisticated than anything developed for any previous mission. We don't have those protocols. We're not close to having them. The biological challenge extends to medicine. A crew on a 40-year voyage will experience the full spectrum of human health issues over that time. Dental problems, broken bones, cardiovascular disease, cancer, possibly exacerbated by the radiation environment, neurological issues, pregnancy and childbirth. If the voyage is long enough to involve generational crew, infections from the ship's microbiome, which will evolve over years in the closed environment of the spacecraft. Every one of these requires medical capability. But you can't bring a full hospital on a spacecraft. Every piece of equipment, every pharmaceutical, every diagnostic machine has to be justified against its mass. Surgeons require practice, tools, and colleagues. A single surgeon, no matter how skilled, cannot perform all possible procedures alone. An anesthesiologist is needed for major surgery, a cardiologist for cardiovascular emergencies, a neurosurgeon for brain injuries. No small crew can include specialists in every field. Training generalists to handle emergencies beyond their training is part of the solution. Telemedicine from Earth is part of the solution. But telemedicine, with a several-year communication lag, is useful for planning, but not for emergencies. A medical emergency in space resolves in hours, not years. The crew handles it with the resources they have, or they don't. Pharmaceutical supplies degrade over time. Many medications have shelf lives measured in months or years. A 40-year voyage would require either enormous stockpiles refreshed through in-flight synthesis or the ability to manufacture pharmaceuticals from basic components. Pharmaceutical synthesis in space, with limited equipment and power for the full range of medications a crew might need, is an engineering challenge that hasn't been seriously addressed. Because we've never needed to. Now, let's think about where alien civilizations would be starting from, and what that means for the probability of a visit to us specifically. The Milky Way is roughly 13 billion years old. Life on Earth is about 3.8 billion years old. Our solar system formed about 4.5 billion years ago, from material already enriched by earlier generations of stars. There are stars in our galaxy significantly older than the Sun. Red dwarf stars, the most common type, with masses well below our Sun's, can burn for tens of billions of years. The oldest known stars in the Milky Way formed within the first couple of billion years of the galaxy's existence. If life can arise around those older stars, if the conditions for life don't require the specific history our solar system had, then civilizations, potentially much older than ours, may have arisen. A civilization that developed technology a billion years before us would have had a billion years to advance. We've had industrial technology for about 200 years. Extrapolating from our 200 years to imagine what a billion years of additional development looks like is essentially impossible. We can't even meaningfully extrapolate 1,000 years of development from our current baseline. A billion years might as well be forever. So the question is, given that such civilizations might exist, why haven't they visited? The most common framing of this question is the Fermi paradox. Enrico Fermi, one of the architects of the Manhattan Project and a physicist of extraordinary intuition, reportedly raised it over lunch in 1950. If intelligent life is common, if civilizations arise across the galaxy over its 13 billion-year history, and if even one of them achieves the capability of interstellar travel, the galaxy should be thoroughly explored or colonized by now. Colonization models show that even at modest fractions of light speed, with reasonable timescales for establishing each new colony before it expands further, the entire Milky Way could be saturated in 50 to 100 million years. The galaxy is 13 billion years old. If anyone started this process even a billion years ago, they've been done for 950 million years. The galaxy should look colonized. It doesn't. The sky is silent. The data shows no megastructures, no engineered stars, no organized patterns that require intelligence to explain. That's the Fermi paradox in its sharpest form. The Drake equation is one way to think about how many civilizations might exist in the galaxy. Frank Drake formulated it in 1961 as a way of organizing the key unknowns. It multiplies a series of probabilities and rates to estimate the number of civilizations in the Milky Way currently capable of interstellar communication. The factors multiply together star formation rates, the fraction of stars with planets, how many of those planets sit in the right conditions for life, how many actually produce it, how many of those go on to develop intelligence, how many build technology, and how long they survive before going silent. Each of those factors is uncertain. For the first few, we've made real progress. The rate of star formation in the Milky Way is estimated at a few solar masses per year. The fraction of stars with planets, once deeply uncertain, is now known to be high. Data from the Kepler Space Telescope and other planet-finding missions has shown that most stars have at least one planet. Planets are not rare. They form naturally from the disks of gas and dust that surround young stars. The number of planets per star in potentially habitable zones is also becoming clearer. Most estimates now suggest that Earth-like planets in habitable zones are relatively common. Not every star has one. But across the hundreds of billions of stars in the Milky Way, there are likely billions of potentially habitable planets. After that, uncertainty explodes. The fraction of potentially habitable planets where life actually arises is unknown. We have one data point: Earth. Life arose here relatively quickly after the planet cooled and liquid water stabilized. Within the first few 100 million years. That might suggest life appears whenever conditions allow it. Or it might mean we were extraordinarily lucky. We can't tell from a single case. The fraction of planets with life where intelligence develops is even more uncertain. Life has existed on Earth for nearly 4 billion years. Intelligence of our type appeared roughly 300,000 years ago. That's a small fraction of Earth's biological history. And even within the history of life on Earth, intelligence of our kind emerged only once. Out of billions of species that have lived here. That might suggest intelligence is rare, even when life is not. The fraction of intelligent civilizations that develop radio technology or equivalent is uncertain. Even among intelligent species, the path from intelligence to technology involves contingencies of culture, environment, and history that we don't fully understand. And the final factor, how long a technological civilization lasts, is perhaps the most important and most uncertain. If technological civilizations tend to destroy themselves within a few centuries of developing powerful technologies, the number of civilizations in the galaxy capable of interstellar contact at any given moment might be very small. Possibly one, possibly zero. If civilizations tend to survive and persist for millions of years, the number could be large. The Drake equation tells us what we don't know as much as what we do know. It organizes our uncertainty. And one of the things we don't know is whether the barriers to interstellar travel are part of the reason the equation produces low numbers. If technological civilizations rarely develop the capability to cross interstellar space, that factor reduces the equation's output. Maybe civilizations arise, develop technology, look up at the stars, calculate the same barriers we calculate, and simply never go. Because it's too hard. Because the cost doesn't justify the benefit. Because the distances are real, and the physics enforces them, and there's no shortcut. That's not a failure of intelligence or will. It's just what the physics permits. The proposed solutions are numerous and span from optimistic to deeply troubling. The rare Earth hypothesis suggests that the conditions for complex life are extraordinarily specific and uncommon. Maybe intelligence has arisen only once, here, and the universe is genuinely empty everywhere else. The Great Filter hypothesis suggests that somewhere in the chain, from simple chemistry to interstellar civilization, there's a step that almost no species crosses. Either we haven't reached it, which would be terrifying, or we've already crossed it, which would be encouraging. The dark forest hypothesis, popularized by the Chinese science fiction writer Liu Cixin, proposes that civilizations hide deliberately because the universe is so competitive that revealing your location is an invitation to destruction. The zoo hypothesis suggests that advanced civilizations are aware of us but have decided not to contact us. There are many others. Each has merits. Each has problems. But one explanation that requires no special assumptions beyond the physics we've already examined is the simplest one. Interstellar travel is so difficult that even very advanced civilizations rarely or never do it. Maybe the galaxy is full of civilizations, each confined to its own star system, each looking up, each wondering, each finding the same answer we find. The distances are real. The physics is the same for everyone. And crossing interstellar distances for any civilization, regardless of its advancement, is so difficult, so expensive, so time-consuming that it remains vanishingly rare, or simply doesn't happen. This isn't a pessimistic interpretation. It's the one most consistent with the physics. And it explains the great silence without requiring any other special assumption. Let's think specifically about what Earth looks like from a distance, because this affects how detectable we are as a potential target for a visit. From hundreds of light years away, our star, the Sun, is visible as a yellow-white star of moderate brightness, in a region of our galaxy that's fairly typical in terms of stellar density. There's nothing about the Sun that distinguishes it from millions of similar stars. G-type main sequence stars are common. Our Sun has maybe 6 billion years left in its main sequence lifetime. It's not particularly young or old by galactic standards. Earth would not be directly visible from hundreds of light years away. At that distance, even with advanced telescopes, Earth would be lost in the glare of the Sun. To detect Earth as a separate object, you'd need to use techniques like transit photometry, where Earth occasionally crosses in front of the Sun and causes a tiny dip in brightness, or direct imaging, using coronagraphs to block the Sun's glare. Transit photometry can tell you a planet exists in our star's habitable zone. It can give you the planet's size and orbital period. With spectroscopic analysis of the light that passes through Earth's atmosphere during transits, you could potentially detect the composition of our atmosphere: oxygen, nitrogen, water vapor, carbon dioxide, methane, ozone. These molecules have specific spectral fingerprints that transit spectroscopy can detect. The combination of oxygen and methane is considered a strong biosignature because in a non-living system, those two gases react with each other and are destroyed. Finding both simultaneously implies something is continuously replenishing them. That something is likely life. Oxygen itself, at the concentrations in Earth's atmosphere, 21%, is hard to explain without photosynthesis. So, a civilization with advanced enough telescopes might detect Earth as a biologically interesting world. But detecting it as home to technology requires something more. The most obvious technological signature we're broadcasting is radio. We've been emitting radio signals for about 130 years. Those signals travel outward at the speed of light, diluting as they spread, becoming increasingly difficult to detect with increasing distance. Our radio emissions are not pointed at other stars. They spread in all directions, omnidirectionally. This means at any given distance, only a tiny fraction of our total transmitted power reaches any particular star. At 100 light years, our early radio broadcasts would be extraordinarily faint. Detecting them would require receivers far larger and more sensitive than anything we currently have. Some researchers have estimated that detecting Earth's radio emissions from 100 light-years away would require a receiving antenna comparable in size to many times the surface area of Earth. That's not a practical technology for any civilization. We might be detectable from nearby, within a few light-years, using extraordinary receivers. But from most of the galaxy, our radio emissions are lost in noise. Our technological existence is essentially invisible at galactic scales. The timing problem is as constraining as the detection problem. Our radio signals have been spreading for 130 years, filled with content, filled with signals that encode the existence of a technological civilization. If a civilization within 130 light-years detected those signals, they detected them recently. Any response has to travel back at light speed. If they sent a signal immediately, it hasn't arrived yet. If they sent a ship immediately upon detecting us, traveling at 10% of light speed, it won't arrive for at least another several centuries. The first possible arrival window for the most nearby civilization that could have detected us and responded instantly is centuries from now. And that's the best-case scenario. For civilizations farther than 130 light-years, they haven't received our signals at all yet. From their perspective, we don't exist as a technological civilization. They might be detecting the Earth of a century or two ago. A planet with biosignatures, maybe, but no radio, no technology. Just another inhabited planet in a sea of inhabited planets. Not an obvious destination for a crewed interstellar mission. The window during which Earth is identifiable as a technological destination is 130 light-years in radius. That sphere contains perhaps a few tens of thousands of stars. In a galaxy with 200 to 400 billion stars. The fraction of the galaxy that knows we're technological is roughly 1 in 10 million. Even if intelligent life is common, even if there are thousands of civilizations in the Milky Way, the probability that any of them are within our detection sphere and are also capable of and motivated to conduct an interstellar visit is small. The question of what biosignatures and technosignatures actually tell us is worth examining carefully, because it shapes the entire logic of whether Earth would be a compelling destination. A biosignature is a chemical or physical sign that life is present. In the context of exoplanet research, it usually means atmospheric chemistry that suggests biology. The most discussed is the simultaneous presence of oxygen and methane. As mentioned, these react with each other in the absence of living processes that continuously replenish them. Finding both in significant quantities in an atmosphere implies continuous biological production. But biosignatures are ambiguous. Oxygen can be produced by non-biological processes. Water photodissociation, where ultraviolet radiation breaks water molecules into hydrogen and oxygen, can produce oxygen in a planet's atmosphere without any life. The hydrogen escapes to space. The oxygen accumulates. This makes oxygen alone an imperfect biosignature. The combination of multiple signals, oxygen plus methane plus nitrous oxide plus certain organic compounds in specific ratios, makes a stronger case for biology. But it's still probabilistic. Abiotic chemistry can produce complex molecules. Distinguishing biological signatures from exotic but non-biological planetary chemistry requires understanding the full context. That understanding is hard to develop from light years away. The point is that even a civilization that detects Earth's biosignatures from a distance knows only that our planet likely hosts life. It doesn't know what kind of life. It doesn't know if that life is intelligent. It doesn't know if the life is producing anything worth traveling light years to interact with. A technosignature is different. A technosignature specifically indicates technology. The most obvious one we're producing is radio. But radio has the detection range problem we've already discussed. It's detectable only at short range with equipment we currently have. Other potential technosignatures include light pollution from our cities, detectable in principle during the planet's night side as artificial light sources, the modification of our atmosphere by industrial processes, changes in chemical composition beyond what biology alone would produce, the modification of Earth's surface reflectivity and heat signature by agriculture and urban development. These are all very subtle changes. They require exquisite sensitivity to detect and clear analytical frameworks to distinguish from natural variation. A civilization 100 light years away, trying to identify Earth specifically as technological, rather than just biological, faces an extraordinary detection challenge. And even if they succeed, they're looking at a planet that was technological many decades ago. The information they have is already old by the time they receive it. The decision to send a mission, based on that old information, commits to a journey that will take additional decades or centuries. The total time lag between what they detected and what they encounter on arrival could easily be a century or more. We're not just hard to find. We're hard to characterize accurately. And accurately characterizing a destination is the prerequisite for deciding it's worth going to. The motive question deserves its own careful examination. Why would any civilization send a crewed mission across interstellar space to another world? The science fiction tropes are curiosity, conquest, and contact. Each of those collapses under scrutiny when you apply interstellar distances to them. Curiosity is real. We're curious about other planets. We've spent enormous resources building telescopes to study them. We've sent probes to the outer solar system. A curious civilization might want to study inhabited worlds. But curiosity has to justify cost. And the cost of a crewed interstellar mission is extraordinary. Energy equivalent to a significant fraction of a civilization's annual output. Material resources and engineering effort on a scale comparable to a civilization's major infrastructure projects. The lives of the crew, committed to a mission with no certain outcome. Against all of that cost, what does a crewed mission provide that an uncrewed probe cannot? An uncrewed probe can be smaller. Smaller means faster and cheaper to accelerate. It can transmit data continuously for decades. It requires no life support, no food, no medicine, no psychology. It can be designed for a one-way trip, reducing the mass requirement roughly in half. For gathering information about Earth, an uncrewed probe is the rational instrument. It's cheaper, faster, longer-lived, and returns more data. The case for a crewed mission requires something a crew provides that a probe cannot: the ability to respond creatively to unexpected circumstances, the ability to conduct complex experiments and make judgment calls in real time, the ability to make contact with us as beings, not just as observed subjects. Those are real advantages. But they have to justify the extraordinary additional cost. And for most scientific purposes, they probably don't. Consider what happens from the perspective of a civilization that has detected Earth and decided to send a mission. They've made the decision. They've committed resources. They've launched a ship, and now they wait. If they're 4 light years away, news of the launch reaches Earth in 4 years. But we don't know they launched, because we're not listening for that specific signal from that specific direction at the right time. Their ship travels. Years pass. Decades. For nearby civilizations, the crew may arrive within a human lifetime. For more distant ones, generations pass on the ship. Meanwhile, Earth evolves. The Earth they detected, with the specific radio signatures that made them think a visit was worthwhile, has changed. By the time they arrive, we may look very different. Our radio emissions may be different. The specific patterns that caught their attention may be gone. We might have switched to fiber optic communication, dramatically reducing our radio leakage into space. Our civilizational priorities might be completely different. The specific political or scientific context that made a first contact scenario relevant to anyone on Earth might be entirely different. They arrive, and they face the situation of any explorer who travels far to meet someone who has moved on. The Earth they find is not the Earth they aimed for, not the Earth they spent decades crossing space to reach, but a different Earth, shaped by decades of additional development they know nothing about. This is a version of the problem that even successful interstellar missions would face. The destination keeps changing during the journey. You can't aim at a moving target that also evolves. You can aim at where the target is, but not at what it will have become. This is especially relevant for missions motivated by specific features of the destination civilization. If you come to study our technology, and our technology has advanced dramatically during your transit, you may find what you came to study is obsolete. If you come to make contact with specific institutions or cultural features, those may no longer exist. If you come to respond to a specific signal we sent, the context of that signal may have dissolved. The impossibility of predicting a destination civilization's future state, combined with the transit time required to reach it, makes targeted interstellar contact missions extremely uncertain in their outcomes, even for missions that succeed at arriving. Conquest makes even less sense. The premise of an alien invasion is that the visiting civilization needs our resources: water, minerals, our biosphere, maybe our planet itself. But any civilization capable of crossing interstellar space already has access to resources in their own star system that dwarf what Earth provides. Asteroid belts, gas giants, rocky bodies of all sizes, the Oort cloud, all of it rich in whatever elements the visiting civilization might want. And in transit between their star and ours, they'd have passed through or near other star systems, each one another warehouse of resources. Earth is not special in what it contains. It's one rocky planet in the habitable zone of one average star. There are billions of similar configurations in the galaxy. Why travel light years to take something from us when the same thing is available everywhere else without the political and military complications? The only possible conquest motive that survives scrutiny is something unavailable elsewhere: our biology, our information, our culture. But those are curiosity items, not strategic resources, and curiosity is better served by observation than by conquest. Now, let's address what a well-developed alien civilization trying to reach us would actually be up against in terms of the combination of all these problems working together. Energy. The energy to accelerate any meaningful payload to interstellar speeds, decelerate it at the destination, and potentially return, is many orders of magnitude beyond what our civilization currently produces annually. Even a civilization, orders of magnitude more energetically capable than us, faces this challenge in proportion to what they want to accomplish. More energy allows faster transit. Faster transit reduces time, but increases the microparticle impact problem because kinetic energies scale with velocity squared. Every increase in speed raises the shielding requirement, which raises the mass, which requires more energy. The optimization problem doesn't have a simple solution. It has a complex surface of trade-offs, with no globally optimal point that makes all constraints simultaneously easy. Biology. Any biological crew faces radiation exposure, microgravity effects, psychological stress, medical needs, food and water requirements, and finite lifespans. These aren't engineering problems with obvious solutions. They're constraints imposed by the nature of biological organisms. A civilization could potentially solve some of them through advanced medicine or biotechnology. Genetic modification for radiation resistance. Pharmaceutical interventions for bone density. Psychological training for extreme isolation. But each solution has limits and introduces new considerations. And you still have the finite lifespan problem. Unless a civilization has solved aging, which is not obviously achievable any more than faster-than-light travel is, the crew ages. A crew that launches young arrives old. A journey long enough requires generations of crew, with all the ethical and social complications that entails. Time. For any destination more than a few light-years away, at any physically achievable speed, the mission takes decades to centuries. During that time, the civilization that sent the mission continues to evolve. Technology advances. Political situations change. The institutional support for the mission may wane. A mission that launches with full civilization-level support might be effectively abandoned decades later when priorities have shifted. The crew returns or arrives at the destination to find a civilization that has changed significantly from the one they left. Maybe to find that their mission has been superseded by a faster technology developed after they launched. Maybe to find that the civilization doesn't exist anymore. The timescales of interstellar travel are comparable to the timescales of civilizational change. That creates a fundamental instability in any mission planning. The SETI experiment, the search for extraterrestrial intelligence, has been listening for radio signals from other civilizations for over 60 years. It began formally in 1960, when astronomer Frank Drake pointed the Green Bank telescope at two nearby sun-like stars and listened for artificial radio signals. He found nothing. In the decades since, many researchers at many observatories on different continents have continued the search. The Parkes Observatory in Australia, the Arecibo telescope in Puerto Rico, which was the world's largest single-dish radio telescope for decades, the Allen Telescope Array in California, a dedicated SETI instrument. The Breakthrough Listen initiative, launched in 2015 with substantial private funding, represents the most comprehensive SETI effort ever undertaken. Using multiple large radio telescopes, it's surveying the sky systematically, targeting millions of stars and nearby galaxies across a wide range of radio frequencies. It's also looking for optical signals. Laser pulses, which could encode information in brief flashes of light, are another potential communication medium. The total coverage of SETI so far, while impressive in absolute terms, represents a small sample of the possible search space. Different frequencies, different signal types, different candidate stars, different times. The search has found no confirmed artificial signal. One famous exception is the WOW signal, detected by astronomer Jerry Eman in 1977 using the Big Ear telescope in Ohio. A strong, narrowband signal at the hydrogen frequency lasted for 72 seconds, matching the expected signature of an extraterrestrial transmission. It was never detected again. Despite many follow-up observations targeting the same region of sky, nothing like it has been seen since. Whether it was extraterrestrial in origin remains genuinely unknown. It might have been. It might have been an unusual terrestrial radio frequency interference event. We don't know. But we haven't heard it again, which limits what conclusions can be drawn. The silence is the data. And that silence is consistent with the picture we've been building throughout this exploration. Civilizations may exist. But communicating across interstellar distances is difficult. The signals dilute. The frequencies are uncertain. The timing of transmissions and receptions across the light-speed delay is a coordination problem without an obvious solution. And the physical visits, the ships, the crews, the journeys, face all the barriers we've described. The galaxy is not obviously teeming with visitors. And when you look at what the galaxy's stars actually look like, searching specifically for signatures of large-scale engineering, the picture is equally quiet. Kardashev's classification of civilizations, proposed by the Soviet astronomer Nikolai Kardashev in 1964, describes 3 types. A Type 1 civilization harnesses the full energy output available on its home planet. We're currently somewhere around 0.73 on that scale. A Type 2 civilization harnesses the energy of its entire home star. Something like a Dyson sphere, a structure encompassing the star and capturing its full output. A Type 3 civilization harnesses the energy of its entire galaxy. These are theoretical constructs, and the boundaries between them are somewhat arbitrary. But they provide a framework for thinking about what evidence we might expect to see. A Type 2 civilization, building a Dyson sphere around its star, would dramatically change the star's observable properties. Instead of emitting light in the visible spectrum, the energy would be captured and re-emitted as waste heat in the infrared. The star would look different from a distance. Dimmer in visible light, brighter in infrared, with an unusual spectral signature. We've looked for this. The Wide Field Infrared Survey Explorer satellite surveyed the entire sky looking for anomalous infrared sources. Nothing convincingly matches the expected signature of a Dyson sphere. One star, KIC 8462-8452, called Tabby's star, showed unusual dimming patterns that were initially proposed as potentially consistent with a partial Dyson sphere or swarm. Later analysis has shown the dimming is more likely explained by asymmetric dust, a natural astrophysical process. The conclusion isn't that Dyson spheres can't exist. It's that, if any exist in the Milky Way, they haven't announced themselves to our surveys. The GHAT survey examined galaxies beyond our own, looking for the signature of civilizations harnessing significant fractions of a galaxy's stellar output. The expected signature would be unusually high infrared emission relative to the visible light output. No compelling candidates were found. Either the galaxy and its neighbors are not populated by Type 3 civilizations, or Type 3 civilizations somehow manage to avoid this signature, or such civilizations don't exist at the scales that would be detectable. The universe looks natural, not managed, not organized, not colonized. Just physics doing what physics does, on an enormous scale, without any visible sign of intelligence at the scales we can survey. That's the data. And it's consistent with a universe where the barriers to interstellar travel are high enough that even advanced civilizations rarely or never cross them. Let me address the argument that we might simply be unable to perceive evidence of highly advanced civilizations. This is a real possibility. A civilization so advanced that its technology is fundamentally different from what we can imagine might produce no signature we'd recognize. The analogy sometimes offered is that you couldn't explain a smartphone to someone in the Stone Age. They'd see it, but have no framework to interpret it. Maybe alien technology is that far beyond us. Maybe we're surrounded by evidence we can't read. This is genuinely possible. It's a real epistemological limitation. We can only search for things we have frameworks to recognize. But here's the problem with that argument as a complete explanation. The most advanced technologies, the ones that would represent true mastery of energy at civilizational scales, produce physical waste signatures that don't require interpretive frameworks. Waste heat is waste heat. Entropy is entropy. Any system that processes energy produces entropy, and entropy has an infrared signature. A civilization processing stellar-scale energy would produce stellar-scale waste heat. A civilization processing galactic-scale energy would produce galactic-scale waste heat. We can measure infrared radiation. We do it constantly. We survey the sky in infrared. We look at galaxy after galaxy, and we see what physics predicts for natural systems, not what physics would predict for managed, engineered systems. The signature of advanced civilizations, if they exist at scales large enough to see, should not require us to understand their technology. It just requires us to detect unexplained energy processing at large scales. We don't. That's informative. Not conclusive, but informative. It's also worth being precise about what would actually happen if a spacecraft from another civilization entered our solar system, because the popular image of disclosure and announcement is somewhat different from how it would likely go. Our detection systems are not comprehensive. We have radar systems that can track objects within a few tens of thousands of miles. We have space telescopes that can image objects in the outer solar system, but only when they're bright enough and our telescopes happen to be pointed in the right direction. We have radio telescopes listening for specific types of signals. We have gravitational wave detectors, particle detectors, and a range of other instruments. But there is no unified system designed to detect an approaching alien spacecraft. Something arriving from interstellar space on a typical trajectory, decelerating gradually, relatively small, and not broadcasting, could potentially enter the inner solar system before we detected it with confidence as artificial. The object 2I 7176/1 Oumuamua, detected in 2017, passed through our solar system without us knowing it was coming. We only detected it because it crossed our survey field of view while already in the inner solar system. Its trajectory was hyperbolic, confirming it originated from interstellar space. Its shape and tumbling motion were unusual. Its outgassing behavior was anomalous. It was briefly, in some circles, speculated to possibly be artificial. Current evidence suggests it was natural, a fragment of a comet or rocky body from another star system. But the episode demonstrated clearly that interstellar objects can enter our solar system without advance notice. We can miss them until they're already here. A second interstellar object, 2I 220 Borisov, was detected in 2019, also natural in appearance. But again, we had essentially no warning of its approach. Our surveying is improving. The Vera Rubin Observatory, when it comes online, will survey the sky more comprehensively and might detect incoming interstellar objects earlier. But even with improved surveys, detecting a deliberately stealthy approach, a small spacecraft not actively broadcasting and designed to minimize its radar and optical cross-section, would be very difficult. None of this changes the fundamental physics of why visitors are unlikely. But it does complicate the popular narrative that we would obviously know if anything artificial had ever entered our solar system. We might know if it was large, bright, or actively signaling. We might not if it wasn't. Let's close the loopholes on communication workarounds. Quantum entanglement is the most commonly cited alternative to radio for faster-than-light communication. Two particles entangled at the quantum level show correlated behaviors when measured, regardless of the distance between them. Measure one particle in a particular way, and the other particle responds instantaneously. This has been experimentally verified. Bell inequality violations, which demonstrate that the correlations cannot be explained by classical hidden variables, have been confirmed in experiments spanning tens of kilometers. The correlations are real, but they cannot transmit information. When you measure an entangled particle, you get a random result. You cannot control what result you get. Neither can your entangled partner. The fact that the results are correlated is only apparent when you compare them. And comparing them requires sending that comparison through a conventional channel, which travels at light speed. No information is transmitted faster than light. This isn't a quirk of our current technology. It's built into the mathematics of quantum mechanics. The no-communication theorem is one of the foundational results of quantum information theory. It has been proven rigorously. It applies to all systems that obey quantum mechanics. And all systems we've ever observed obey quantum mechanics. Entanglement is fascinating. It's the basis for quantum cryptography, which allows secure communication. It's the basis for quantum computing, which will allow faster computation for specific types of problems. But it is not a backdoor around the speed of light. Not for us. Not for anyone. Neutrinos are another candidate that sometimes comes up. Neutrinos pass through matter almost completely unimpeded. They travel at very close to light speed. They could, in principle, carry information through objects that would stop radio waves, through planets, through stars. But transmitting information via neutrinos requires generating enormous quantities of them in a controlled pattern and detecting them at the destination. Neutrino detectors are massive underground tanks of water or ice, or huge volumes of liquid, because neutrinos interact so rarely. Even with detectors the size of the Ice Cube Neutrino Observatory at the South Pole, which instruments a cubic kilometer of Antarctic ice, the detection rate for natural neutrinos is modest. A deliberate narrowband neutrino transmission from another star system would be extraordinarily difficult to both generate and detect. Neutrinos travel at close to light speed, but not faster than it. So they don't offer a speed advantage over radio. And they're much harder to work with. They're not a practical improvement over radio for interstellar communication. There's one more dimension to this problem that doesn't get enough attention. The problem of contamination. If an alien civilization arrived at Earth, they would be carrying biology. Not necessarily life in the science fiction sense of bacteria lurking in their ship's pipes, but the chemistry of their origin, organic compounds, molecules that evolved in a different biosphere, possible microorganisms adapted to their world, now encountering ours. And conversely, Earth's biology would encounter them. We know from our own history how devastating the introduction of biology between isolated ecosystems can be. When European explorers arrived in the Americas, they brought diseases against which the indigenous population had no immunity. Smallpox, measles, influenza. The effect was catastrophic. Estimates suggest that somewhere between 50 and 90% of indigenous American populations were gone within decades of sustained contact, primarily due to disease. The populations of Australia, of the Pacific Islands, of countless isolated communities suffered similarly when exposed to diseases their immune systems had never encountered. Biological isolation produces biological vulnerability. Now scale that principle to interstellar contact. An alien civilization would have biology evolved over billions of years in a completely separate biosphere. Their biochemistry, if it's based on similar principles, carbon-based, water-solvent, with amino acids and nucleic acids, would be related enough to ours to potentially interact. Alien microorganisms, evolved to exploit their world's chemistry, might find Earth's biology exploitable too. Or Earth's microorganisms might devastate theirs. The idea of protective quarantine protocols for a visiting alien ship seems obvious in retrospect. But implementing them in practice is extraordinarily difficult. How do you contain a civilization-sized biological threat? How do you quarantine an entire ship's worth of biology while still enabling meaningful contact? How do you prevent any exchange of microorganisms when the physics of gas and liquid involves essentially continuous molecular exchange in any environment two organisms share? These aren't hypothetical concerns. They're real biosecurity challenges that have no clear solutions. Any responsible approach to interstellar contact from either direction would have to grapple with them. And a civilization advanced enough to cross interstellar space is presumably advanced enough to recognize the biological risks of contact, which might be another reason to prefer robotic probes over crewed missions. Probes carry no biology. Probes don't contaminate. Probes can be sterilized to whatever standard is achievable. The biological contamination problem is one more factor pushing rational advanced civilizations toward robotic contact rather than crewed visits. Every proposed workaround for the light speed limit, when examined carefully, either doesn't actually exceed the light speed limit or requires exotic physics that appears to be forbidden by the universe's fundamental structure, or requires energy on scales that no civilization appears to have achieved. The light speed limit is consistent. It applies everywhere we've looked. It applies in every experiment we've conducted. It's the most thoroughly tested constraint in physics. Everything we've discussed applies equally to any civilization considering the journey. We're not uniquely disadvantaged by our position or our current technology. The physics doesn't provide different rules for civilizations that have been around longer. The speed of light is the same for everyone. The rocket equation gives the same answers for everyone. The radiation is the same for everyone. The distances are the same for everyone. A civilization that has been developing technology for 1 billion years longer than us has had time to make those technologies extraordinary. But extraordinary within the constraints of physics, not outside of them, unless we discover that the constraints themselves are wrong. Unless the physics we believe describes the universe turns out to be an approximation to something deeper. That's always possible. Physics has surprised us before. Relativity overturned classical mechanics. Quantum mechanics overturned the deterministic clockwork universe. The discovery of dark energy in the late 1990s overturned the assumption that the universe's expansion was decelerating. New physics could appear. Maybe it contains loopholes we can't currently see. Physicists take this seriously. They continue to probe the foundations of our understanding, looking for inconsistencies, looking for phenomena that don't fit the current framework, because that's where new physics hides. But we can only work with what we know. And what we know, right now, is that the barriers to interstellar travel are genuine, physical, and apply to everyone. Proposing that sufficiently advanced alien civilizations have broken through them requires proposing that physics we don't know about exists and that it provides solutions we haven't modeled. That's possible, but it's not evidence of anything. It's a statement that we could be wrong about physics, which is always true, but which doesn't tell us where the new physics is or what it says. There's something quietly profound about where all of this lands. The universe appears to be a place where the most natural consequence of the laws of physics is isolation. Not permanent isolation. Not absolute isolation. But functional isolation on timescales that matter to civilizations. Every intelligence that arises in the Milky Way, wherever it is, faces the same geometry, the same distances, the same speed limit, the same trade-offs between speed, energy, and biological survivability. And the most likely result of all those constraints, if they're as firm as they appear to be, is a galaxy populated by civilizations that develop in isolation, communicating, eventually, across the light-speed delay, but physically visiting each other only in the most exceptional circumstances, if ever. This is not the picture science fiction gave us, but it's the picture physics gives us. And physics is more reliable than fiction. The great silence, the absence of obvious alien contact, becomes less mysterious in this picture. Not less profound, but less surprising. If everyone is in the same situation, if every civilization in the galaxy faces the same barriers, then of course the sky is quiet. Not because no one is out there, but because the barriers are real for everyone. Everyone is in the same boat. The same, very slow, very expensive, very dangerous boat. The historical context of our own civilization's interest in alien contact reveals something interesting. We've been thinking about interstellar contact seriously for less than a century. Radio astronomy began in the 1930s. The first systematic proposal to listen for alien signals came in 1959 in a paper by physicists Philip Morrison and Giuseppe Cocconi. The first actual listening experiment, Project Ozma, was conducted by Frank Drake in 1960, 66 years ago. In cosmological terms, that's nothing. Our species, Homo sapiens, has existed for about 300,000 years. Our genus, for about 3 million. Life on Earth, for about 3.8 billion. The galaxy for about 13 billion. We've been seriously searching for alien contact for 66 years. Out of 3.8 billion years of biological existence on this planet. If you compressed Earth's biological history into a single year, our SETI program would have been running for less than half a second. We haven't found anything. But drawing conclusions from half a second of a year-long experiment is not statistically meaningful. The sample is not representative. The search is ongoing. Our sensitivity is improving. The range of frequencies and signal types we can detect is increasing. The number of stars we can survey with meaningful sensitivity is growing. Breakthrough. Listen. The current most comprehensive SETI program has increased the amount of sky surveyed and the depth of that survey by factors of many compared to what was possible a decade ago. New radio telescope arrays are being planned and built. Optical SETI, listening for laser pulses rather than radio waves, is a growing field. We are genuinely not close to having searched comprehensively. The full parameter space of possible signals, frequencies, directions, polarizations, encoding schemes, intensities, is enormous. We've barely begun. So the current silence shouldn't be interpreted as strong evidence that no one is there. It's more like having checked a small corner of a vast library and finding nothing on the specific shelf you looked at. That's data, but not comprehensive data. The silence will become more meaningful as our search becomes more comprehensive. If, in 100 years, with instruments far more sensitive than anything we have, searching a much broader range of signals across a much larger portion of the sky, we still hear nothing, that will be a more significant result. For now, we're early in the search. And the absence of a confirmed signal is consistent with both a galaxy that's genuinely quiet and a galaxy we haven't searched adequately. Both are live possibilities. And most of them, probably, haven't launched it, or have launched only probes, or have decided that the cost doesn't justify the mission given what they can learn from remote observation, or are still working on the problem, as we are. When you step outside tonight and look up at the sky, you're looking at the surface of this reality. Every star visible to the naked eye is inside our own galaxy. Every one of them is, in operational terms, enormously far, not in the poetic, hand-waving way. In the specific, calculated, physics-constrained way that means getting there from here, carrying anything meaningful, would require technology and energy and time we don't have. And almost certainly, any civilization there doesn't have either. Not the combination of all of them together. Not in a form that makes visiting us worthwhile relative to the cost. The silence isn't hostility. The absence of alien visitors isn't a mystery that demands a dramatic explanation. It's what you'd expect from a universe where the distances are real, where the physics is honest, and where everything, every civilization on every world, lives under the same rules. Separated by the same gulf, facing the same walls, looking up at the same stars, wondering the same things, and finding the same answer. Not hopelessness. Not certainty that nothing exists beyond us, but an honest reckoning with what the universe actually is. An enormous, ancient, mostly quiet place, where light itself takes thousands of years to cross from one interesting thing to the next, where the question of whether anyone will ever close that distance, in person, in ships, carrying living minds from one star to another, remains genuinely open. But where, for now, in this moment, the sky is quiet, and the physics says it's likely to stay that way for a very long time. That's not a failure of the universe. It's the universe being exactly what it is, something vast and old and indifferent to our wishes, something that doesn't apologize for the distances, something that enforces its rules without exception. And yet, we keep looking up because the stars are there, because they're real, because somewhere in that extraordinary silence, other minds may be doing the same thing, looking up at their own sky, wondering, finding the same answer, and feeling, perhaps, the same strange combination of loneliness and kinship, not with anyone nearby, but with the universe itself, which contains us and them and the distances between us all, and has never once promised that those distances would be easy. Good night.